Hello, my name is Sean Prendeville. Welcome to Fourier methods in combinatorial number theory. So just before we start, if you have any accessibility issues while you're studying this course, whether that's the videos or the notes, drop me an email and we'll try and resolve those. The notes for the course are available on the course webpage, and I'll email them around each week preceding the lecture. So the structure of this course is I'm going to give these videos where I'll provide sort of a big picture, and it'll be quite fast and loose with rigor and details. And I've relegated all the details to the notes. And that's because I find it quite hard to follow details in talks, and I prefer to see a big picture. And many of you are very talented graduate students and beyond, and I would hope that you could reconstruct the details of the arguments I'm going to present if you needed to, given that you know what the essential ideas are, and with the help of Wikipedia. Okay, so I'm hoping to communicate the underlying ideas. So the outline for today is we're going to start by motivating why you might be interested in combinatorial number theory and why you might be interested in the Fourier-analytic approach to combinatorial number theory. And the sort of paradigm throughout this course is we're trying to count solutions to a linear equation in some set of integers where we don't know anything about the set apart from its density. It's got, say, positive density. So how many solutions to an equation should you expect in such a set? We'll first discuss the naive heuristic, a heuristic ballpark figure of the order of magnitude. And then we'll talk about when that naive heuristic goes wrong. What are the possible obstructions to the naive heuristic holding? Now, this course is also about Fourier analysis, and Fourier analysis is there because it allows us to detect these obstructions to the naive heuristic. Okay, and when there are no obstructions present, we call a set Fourier uniform. And we'll show that this notion is quite useful because if you are given a Fourier uniform set, if you know nothing about it apart from its density and the fact that it's Fourier uniform, you can obtain an asymptotic formula for the number of solutions to an equation where the variables come from that Fourier uniform set. So Fourier uniform sets satisfy this naive heuristic. They have the sort of heuristic order of magnitude when you're counting solutions to an equation in that set. So why combinatorial number theory? Well, I'd hope you'd agree that we all would like to solve certain equations involving prime numbers. So the first few equations there, we've got the twin prime conjecture, binary Goldbach problem, Landau's fourth problem. The fourth equation is the ternary Goldbach problem. Every large odd integer is a sum of three primes. So unlike the first three equations, we know the fourth equation has solutions in integers. And here's an equation we're going to meet again and again in the course. It's the equation of three-term progressions. You can parameterize solutions to this equation as x plus d, x plus 2d. So the variables solving this equation constitute a three-term arithmetic progression. And it's an old result of van der Korpe that the primes contain infinitely many of these three-term arithmetic progressions. Okay, so we'd all like to solve equations in prime numbers. Some we can, some we can't. But if you want to get a handle on why certain equations should possess solutions in prime numbers, perhaps you can ask a more general question. So this is a well-used meta principle in mathematics. If you're attacking a problem, maybe generalize the problem to get an insight into the special case. So the type of generalization we do in combinatorial number theory is we move away from this concrete set of integers, the primes, and we just assume we've got a subset of integers which has a similar density to the primes, logarithmic density. So here this square brackets n is my notation for the interval of the first n positive integers. Now, given this combinatorial hypothesis, can you deduce something in number theory? We're talking about combinatorial number theory. Can you deduce that your set possesses some arithmetic structure, like an arithmetic progression of length k? So we don't know the answer to this question, apart from a very recent result of Bloom and Sisask, which resolved this for 3-term arithmetic progressions. So that tells you something about prime numbers as well, although we knew that the primes contain infinitely many of these 3-term progressions long before the result of Bloom and Sisask. Okay, but if you're interested in longer progressions, this question seemed hard. So generalizing hasn't bought us anything. But you might try another meta principle. You weaken your hypotheses to gain an insight into the stronger form of the question. So let's weaken our density assumption, removing logarithmic density and assuming that we've got positive density. Say we occupy a positive proportion of the interval as the parameter, the length of the interval, n, tends to infinity. So we're occupying, say, 1% of the interval. Then are you guaranteed to contain a k-term arithmetic progression in your set? So the answer to this is yes, and it's a cornerstone of combinatorial number theory. It's Szemeredi's theorem. And it's a beautiful result. It's got lots of different proofs. And I think those proofs are interesting because they give you an insight into why a set should contain arithmetic progressions. And maybe having answered this more general question, or a variant on your original question about do primes contain k-term arithmetic progressions, you might hope you can then use some of these ideas for this analogous problem to say something about k-term progressions in primes. And this is broadly similar to the historical narrative that led to the Green-Tao theorem, where in Green-Tao's original proof, they use insights from the various proofs of Szemeredi's theorem, together with Szemeredi's theorem as a black box, to show that the primes contain k-term arithmetic progressions. So one reason you might be interested in combinatorial number theory is because it gives insight into these questions of specific arithmetic interest, solving equations in interesting sets like the primes. What about Fourier analysis? Well, when you prove Szemeredi's theorem, it's immediately apparent that sets contain arithmetic progressions for very different reasons. And any proof of Szemeredi's theorem has to contend with these different reasons. Some sets contain arithmetic progressions, APs, because they look like random sets. And so you have lots of collisions, so you're very likely to contain an arithmetic progression. Some sets contain arithmetic progressions because they're more structured. They've got some algebraic structure. And there's the argument exhibiting progressions in these algebraic-like sets is different from the random case. Now, Fourier analysis and higher order variants of Fourier analysis quantify how random a set of integers looks. So you take a deterministic set of integers, how much does it look like a random set? So I like to think of this notion of Fourier uniformity, which we're going to introduce today. It gives you a scale where sets which are very Fourier uniform are very random or random-like. Sets which aren't Fourier uniform have some algebraic structure. And in higher order Fourier analysis, you have sort of higher order notions of uniformity. And as I say, it's easy to show that sets which look random-like contain many 3-term progressions. Sets which look algebraic-like contain many 3-term progressions. But what do you do in the hinterland? In this kind of limbo between the two extremes? So what I find particularly interesting over the last 20 or so years is methods have been developed which allow you to decompose a set of integers into sort of algebraic pieces. And on each algebraic piece, your set behaves pseudo-randomly. So I sort of call this a decomposition theorem, or people call this a decomposition theorem. So it really divides your problem up into lots of little algebraic problems, or one big algebraic problem. And within each algebraic fiber, there's a random problem. And you solve both of those problems, and you can stitch those solutions together to exhibit arithmetic progressions in a dense set by solving the random case and solving the algebraic case. And then the decomposition theorem allows you to stitch those two extremes together. So we're going to see about 4 instances of results which have this decomposition flavor. And my main learning objective in this course is to give you a sense of these decomposition theorems. I'm not so interested in the applications. although they're nice, but I want to impart this sort of decomposition philosophy. So just a word on Fourier analysis. Fourier analysis allows us to count solutions to a single equation in at least 3 variables. So we need the coefficients to be non-zero and the number of variables to be at least 3. And I mentioned higher order Fourier analysis, and that's good for systems of equations. So a single equation can encode a 3-term arithmetic progression, and a 4-term progression needs a system of equations to be encoded. If you want to study 4-term progressions, you have to move to higher order Fourier analysis. Fourier analysis can cope with systems of equations in sufficiently many variables, provided the number of variables is twice the number of equations plus 1, and maybe you assume some non-singularity conditions on the coefficients. But when you get smaller numbers of variables, like with 4-term progressions, then you need to move to this higher order notion of Fourier analysis. And essentially, what that means is there are different algebraic obstructions to having the random, to being random, or random-like. But we're going to stick to Fourier analysis. So our aim in this course is to try and count solutions to an equation like equation 1, given a dense set of integers. So it's a set in this interval 1 up to capital N, and all we know about it is its density delta. We don't know anything else. How can you count solutions to an equation in such a dense set at this level of generality? So let's talk about the sort of answer you should expect. And we're going to restrict ourselves to a very simple equation, x plus y equals z. How many triples solving that equation should a dense set of integers possess? So what size is this count? The number of triples x plus y equals z, solving our equation, and where the variables come from our dense set A. So solving our equation is like representing 0 by this linear form, x plus y equals x plus y minus z. What's special about 0? You might expect that provided this linear form, x plus y minus z, isn't biased to, say, being even or to being large, you might expect that for most possible values the linear form could take, it takes values in this interval minus n up to 2n when the variables come from the interval 1 up to n. You might expect there's nothing special about 0, and the order of magnitude of this sum, representing 0 in our dense set, should be the similar order of magnitude to representing a number c. Now, as you get to the extremes of the interval, you would expect fewer representations, but in the majority of the interval, maybe you expect a similar order of magnitude. So given that assumption, this symbol here means order of magnitude. It means within a multiplicative absolute constant, a lower bound and an upper bound. Given that assumption, you can average the right-hand side. So let's sum over all possible values of the linear form and normalize by the length of this interval, by the number of possible values. That's my notation for this expectation operator. So if you believe this heuristic, you should definitely believe this heuristic. But by averaging, we've removed the constraints in this equation. We're summing over all possible values of the linear form. And what that's really doing is just summing over all elements of the set. So these variables x, y, and z are now free to roam over the set A. We've introduced a normalization factor, which is of order 1 over n. So we get the number cardinality of our set cubed divided by the length of the range up to orders of magnitude. And if you're interested in densities, you could write this as delta cubed times n squared. So the naive heuristic predicts that the order of magnitude of this number should scale quadratically with the length of the interval, n squared, and it should scale cubically with the density of the set. How reasonable is that heuristic? So it's a reasonable heuristic for a random set of integers. So here's my random model. I choose a subset of the interval 1 up to n by selecting elements independently with probability delta. The expected size of this set is then delta times n. So you could think of this as a model for a random set of density delta. Let's maybe calculate the expected value of the number of solutions to our equation. Because the expectation operator is linear, you can crash through the sum and you replace this product of indicator functions with a probability. You're summing over all triples solving the equation in your interval, weighted by the probability that all the variables lie in your set A. Provided x, y, and z are distinct, this number is going to be delta cubed. And indeed, almost every solution to this equation has distinct variables. So the set of solutions where two of the variables coincide is a sparse set of solutions. So you can easily show that for the majority of solutions, this number is delta cubed. So we get that the number of solutions in our random set is equal to the number of solutions in the interval scaled by a factor of delta cubed. And just to say that the number of solutions in the interval, you can easily calculate that to be half n squared up to lower order terms. That's a nice exercise. Okay, so it seems like these random sets obey the naive heuristic, at least in expectation. So let's test this experimentally. So I'm going to take the interval of the first 200 positive integers, and I'm going to choose a random subset of cardinality 20. So its density is 0.1. I am selecting 10% of the interval randomly. The number of solutions in the full interval is 19,900. So the naive heuristic predicts that the number of solutions in this random set should be 1 over 10, that's the density cubed, times 19,900, that's approximately 20. So let's see if that's reasonable. So here's our first random set. You can see it sort of looks like what you'd expect a random set to be. There's lots of clustering. There's some moderate gaps, but there's no gap, massive gaps. The points sort of appear everywhere along the line. And the number of solutions, provided you're not watching this video on a phone, is 19 in this particular random set. And we said the naive heuristic predicts 20 solutions. So that's pretty good. Another random set gives you 17 solutions. Another random set gives you another 17 solutions. A third random set gives you 28 solutions. Now I contend that the naive heuristic is still pretty much valid because all these numbers are of a similar order of magnitude. Remember, the density is 1 over 10. So we're talking in orders of 10. Or you could have much fewer solutions, 12, but these random sets seem quite robust. You always get between 10 and 30 solutions to your equation in general. So it seems very unlikely that you get no solutions, and it seems very unlikely that you get 100 solutions. So now let's test the naive heuristic for some structured sets. So this top line is just to remind you of what a random set looks like, because I want to show you some more sets which definitely don't look random. So here's our first structured set. It's very regular. It's an arithmetic progression of common difference 10, starting at the number 10. How many solutions do we get? Well, now we get an order of magnitude more. We get 190 solutions to our equation. So maybe structured sets always give you way more solutions than random sets. Maybe random sets are the worst example. Well, that's not the case. Here's a very similar looking structured set. Again, common difference 10, this time starting at 5. Now we've got 0 solutions. So the point I'm trying to make is that these structured sets, they might have loads of solutions, they might have few solutions, but whatever they have, the number of solutions is way off the naive heuristic, an order of magnitude different from the naive heuristic. Here's another structured set. The first 20 integers, a subinterval. And again, we get 190 solutions. You could choose a different subinterval and you get 0 solutions. Now, these sets are quite interesting. They look randomish, but there's some repulsion there and some regularity. So to me, this looks like an interleaved progression or a union of a few arithmetic progressions. So you can sort of see some arithmetic progressions maybe emerging where, up to little changes of plus or minus 1 or 2. So it looks like a union of some approximate arithmetic progressions. And we've got loads of solutions, 139, an order of magnitude larger than naive heuristic predicts. And you can get similar looking sets. This looks like a shift of the previous example, but it's not a shift of the previous example. And it's got 0 solutions. So what I want to try and demonstrate is that all of these structured examples are essentially instances of exactly the same phenomenon, what we're going to call Bohr obstructions. And these Bohr obstructions, if a set has this Bohr structure, the naive heuristic can't hold. Hope to demonstrate that. And if there are no Bohr obstructions, then the naive heuristic should hold. Okay. So let's show that even though these sets look very different from the perspective of looking at a line, we're going to view these sets differently and they'll all look the same. How do we view them differently? Well, what we're going to do is we're going to embed them into the circle. We're going to embed the interval of the first 200 integers onto the circle. We're going to embed it homomorphically. So just to remark, every homomorphism from the additive group of integers to the multiplicative group of complex numbers with absolute value 1, i.e. the unit circle under multiplication, takes the above form, this form here. So what is this form? N, the integer, maps to E alpha of n. So E alpha of n is a notation common in analytic number theory, where E of alpha means e to the 2 pi I alpha. So you can check every homomorphism takes this form. Essentially, your e to the alpha is choosing a point at angle alpha on the unit circle if we're measuring a full rotation as having angle 1. So you're taking this as your initial point. 1 is mapping to this point. And then, we've got a cyclic group which generates itself from a single generator. So that's how you show all the homomorphisms take this form. We're going to call this variable frequency, which determines the homomorphism. We're going to call that variable the frequency. Let's write that. It's the frequency. And the homomorphism, the frequency can be any real number, but it's uniquely determined by the congruence class of alpha mod 1. So determined by alpha mod 1. So this frequency is really, or these homomorphisms are indexed by frequencies lying on the real numbers modulo the integers, which we is a set we denote by T for the torus. Okay, that's the homomorphism. So we take our interval of integers, we wrap it around the unit circle in the complex plane. So this is, the circle I've drawn here is one particular example of such an embedding for a certain specific frequency. I think this is for alpha equals to √2. So this is what we get. Oh, here we go. Alpha is equal to √2, that's the frequency. We embed the interval of integers around the unit circle. Now this set, which looked like an interleaved progression, The way I've constructed it is, given this homomorphism, I've taken a neighborhood of 1, a neighborhood of the identity, an arc around 1 in this group, and I've pulled it back to the integers. So one way of writing this down is, it's a set of integers such that when you map n, you map the integer n, you multiply it by root 2 and reduce mod 1. The distance to the nearest integer is at most 1 over 20. So what that's saying is this angle here is 1 over 20. And the angle here is 1 over 20, where we're measuring a full rotation as having an angle of 1. So we're going to write all of these examples down using this notation because it makes these things look like what we're going to later define as Bohr sets. So this is our first example. So by pulling back this neighborhood of the identity, we got a set here which had way more than the naive heuristic number of solutions. Why did it have loads more solutions? This is where the algebraic structure comes in. It has more solutions because if you took two angles, theta 1 and theta 2, two angles in this arc, then you add theta 1 to theta 2, maybe you get a new angle. This is theta 1 plus theta 2. And it's very likely that the sum of theta 1 and theta 2 lies in the same arc, is at most 1 over 20. So adding angles in this region, you're very likely to stay within the region. So when you pull back via a homomorphism, if you sum two integers in that set, you're very likely to stay in the set. And that's why you generate lots of solutions to your equation. How would you generate very few solutions? You would pull back a different arc, maybe this arc over here, or this arc, a neighborhood of -1. And here, when you add angles in this region, you're very likely to add two angles in this region, and you're very likely not to remain in the region, in the arc. So adding angles here in this arc takes you out of the arc. And in fact, you have 0 solutions by adding angles in this arc. So when you pull back via a homomorphism to the integers, and you add two integers in the corresponding set, you're never going to still remain in the set. So you don't have any solutions to this equation. So defining the naive heuristic so far looks like a matter of embedding in the circle and pulling back an arc. And actually, that is essentially the only obstruction to the naive heuristic. So how do I unify all the examples we saw previously? If you wanted to look at the lower interval, 1 up to 20, you choose a different frequency, 1 over 200. If you embed the whole 1 up to 200 around the circle using this frequency, you go all the way around the circle. But this arc corresponds to the first 20 integers. So I contend this is an example of some Bohr structure, where what I mean by Bohr structure is you take an arc and you pull back to the integers via a homomorphism. Okay, so the interval can also be described as a Bohr set. And so can this interval here, where we've got no solutions. Again, because we're taking an arc far away from the identity. And you can write that down in terms of this distance to nearest integer function. A progression, well, when you wrap the whole interval according to the frequency 1 over 10, you get 10 evenly spaced points around the unit circle. And if you pull back a neighborhood of the identity, you're essentially pulling back a single congruence class, mod 10, and that gives you this homogeneous progression starting at 10. And we've said arcs around the identity have lots of these additive triples. And arcs away from the identity have very few additive triples. So let's give the formal definition of a Bohr set. So again, this is my reminder that we're working on the torus. That's where our frequencies come from. And you can measure the distance from a frequency to the identity of this group by this distance to nearest integer function. So a one-dimensional Bohr set is a set of integers corresponding to pulling back the arc around 1 in some epsilon neighborhood. Let's write that a bit more carefully. You take your circle, you take some angles epsilon, and you pull back the corresponding arc. That's a one-dimensional Bohr set with frequency alpha and radius epsilon. Radius is the angle. A d-dimensional Bohr set is an intersection of d copies of a one-dimensional Bohr set with different frequencies, but the same radius. Using this notation, a Bohr translate is just taking a different arc, not necessarily an arc around the identity. So a Bohr translate would be, you've got your circle, and you take a different arc and pull that back to the integers homomorphically. A d-dimensional Bohr translate is when we take a Cartesian product of intervals, and alpha here is a vector, a d-dimensional vector of frequencies. Okay, that's what I'm going to call a Bohr translate. So we're interested in solving equations in dense sets of integers and counting solutions to equations in a dense set of integers. And Bohr sets are examples of dense sets of integers because we prove in the notes that Bohr sets are dense. And you can obtain a uniform lower bound on their density, which is uniform in terms of the frequencies. It doesn't really matter about the frequencies. The density only, the lower bound on their density depends only on the radius and the dimension. Okay, so imagine you're given an arbitrary set of integers. How do you check whether it's a Bohr set or not, or whether it's a Bohr translate? So I'm going to exhibit a test for Bohr structure using a Fourier analysis. We won't define the Fourier analysis yet, but I just want to motivate the definition of the Fourier transform. So let's try and test for Bohr structure. So we said Bohr structure is what you get when you take an arc and pull back under a homomorphism. So if we're given a set of integers and we want to see whether it looks like a Bohr set, one thing we could do, or a Bohr translate, is embed it in the unit circle, try all different homomorphisms, i.e. try all different frequencies for our embedding. And if we ever get an arc, we know we've got a Bohr translate. Okay, so let's do that. Start at the frequency 0. Now it looks like for these low frequencies, we've got an arc here. We're done. This is a Bohr set. But what you'd find is, because these frequencies are so small, so much smaller than 1 over the length of the interval, so these are much smaller than 1 over the length of the interval, at these very small frequencies, all subsets of 1 up to 200 are constrained to these arcs. Now they might be distributed in these arcs in different ways, but they're always constrained to this initial arc. So you might always look like a Bohr set at these low frequencies. So we need to get up to a frequency where we can sort of go all the way around the circle. Okay, and the first frequency at which we can travel all the way around the circle is 1 over 200. And that's true for any subset of 1 up to 200. So now we're all the way around the circle. Do we look like a Bohr translate? No. We're spread around the circle. We're not concentrating in an arc. So still no Bohr structure. Let's go through some frequencies. And there's little bits of clustering, but we're not clustering in a single arc. So I would contend we don't have any Bohr structure yet. Because these points are spread evenly around, almost evenly, sort of equidistributed or uniformly around the unit circle. You can have some pseudo clustering, but the clustering is distributed nicely. We're not in one single arc. Okay, so we'll go through these numbers. Now you can see there's a large gap emerging. So I would contend we're getting more and more clustering. And indeed, at this frequency 0.414, we seem to have occupied almost all of an arc. And there's no coincidence in that, because this number is approximately equal to √2 modulo 1. And the way I constructed this set was as the inverse image of an arc corresponding to the homomorphism given by the frequency root 2. So we've detected some clustering by running through the frequencies. You go beyond the frequency root 2 and it seems like we're spreading out around the circle again. Some local clustering, but we're not clustering in a single arc. You carry on going through the frequencies. The last frequency you need to worry about is 1/2. The only possible points on the circle you can occupy at the frequency 1/2 are 1 and -1. And again, we're distributed evenly in those two possible points. So no Bohr structure here, but we detected some earlier Bohr structure. So I said there's this test, Fourier uniformity, which detects this Bohr structure. So to define the Fourier uniformity, or this notion of Fourier uniformity, we need to define the Fourier transform. You take a function on the integers, finitely supported, so this sum makes sense. You sum your function and you twist it by the homomorphism evaluated at each integer. So the Fourier transform at the frequency alpha is what you get when you twist your sum, when you integrate your function and twist by this homomorphism corresponding to the frequency alpha. Again, e of alpha is e to the 2 pi I alpha. So these are points on the unit circle. So this looks a little hard to parse for an arbitrary function, but for a specific function, for a specific set of integers, it's sort of more easy to understand what's going on. We are literally embedding our set in the unit circle via one of these homomorphisms and then adding all the points up. So if your set is spread evenly around the circle at this frequency, then when you add these vectors up, the vectors all point in different directions and those directions all cancel out and you get a small sum. So when there's no clustering, no Bohr structure, you should have a small Fourier transform. When these points cluster, when there's a little bit of Bohr structure, a lot of these points point in the same direction, so you add them up and you get a large vector pointing in a similar direction. So the Fourier transform of your set is large. But of course, I said for very low frequencies, you always have clustering, but so does the whole interval. So this is the set of points corresponding to the full interval 1 up to 200. This is the set of points corresponding to our subset of the interval. And both cluster in this arc because they're forced to cluster in this arc. So to give a nice definition of when we've got some clustering or not, what we do is we compare the Fourier transform of our set normalized. This is some normalized Fourier transform. We compare it to the normalized Fourier transform of the interval. And if those two sums point in the same direction, then this difference should be small. And if the vectors are very different, this difference should be large, difference in direction or magnitude. So we say a set is epsilon Fourier uniform if for any frequency, any possible homomorphic embedding in the unit circle, the average of our points of our set is equal to the average of the points in the interval up to epsilon. So with our normalization of Fourier transforms, another way of writing this down is the Fourier transform of our set is comparable to a normalized Fourier transform of the interval, where the normalization is the density of our set up to epsilon. So this coefficient at 0 is the largest our Fourier transform could be. So that's the definition of epsilon Fourier uniform. So what I'm sort of trying to suggest is that if you're epsilon Fourier uniform, you don't have any Bohr structure. So just a word of what this looks like, the Fourier transform of the interval. Well, here's a graph, a plot of it for the interval of length 200. And you can see that most of the time it's essentially 0, this normalized Fourier transform. So it is true to say or it's almost true to say to verify that a set is Fourier uniform, you just have to show its Fourier transform is small everywhere. Apart from, if we enlarge this graph here, apart from when we're at very low frequencies, so this is the interval 0 up to 1 over 200. And at these low frequencies, our definition is that not that the Fourier transform is small, but that it's distributed in the sub-arc in the same way as the interval is. And so you can account for that by comparing with the Fourier transform of the interval. So here's a random set of integers with only 19 solutions to our equation. Here's the full set of the interval of integers. Let's have a look at how these Fourier transforms compare as we vary frequencies. So as we say, at first, they're both constrained to the same sub-arc, and they're distributed in a similar manner in these sub-arcs. So after normalization, you get two vectors which should be comparable. That's for low frequencies. We eventually spread out around the circle. Now the interval is fully spread around the circle at all higher frequencies. So, I mean, the Fourier transform of the interval is now going to be small everywhere if it's always spread around the circle evenly. So once we're past this, these low frequencies, to check that our set is Fourier uniform, we just need to have equidistribution around the circle. And indeed, we do have that. As we vary through the frequencies, you can see there's some micro clustering, but mainly equidistribution around the circle. Okay. So you can, these obstructions to the naive heuristic, where we obtained loads of solutions or very few solutions to our equation, an order of magnitude different from the naive heuristic, you can account for that by showing that these sets are not Fourier uniform. So this set here is equal to the Bohr set obtained by intersecting this infinite Bohr set with our interval of integers. And because of its definition, you can see it's got a large Fourier coefficient at root 2. This is what the distribution of the points on the circle at that frequency. And they all point in the same direction, whereas the interval of integers, all these directions cancel out. So this has a small Fourier transform at the frequency root 2. Again, this other Bohr set, Bohr translate now, with very few solutions, it also has a large Fourier coefficient at root 2. The interval doesn't. The progression, this has a large Fourier coefficient at the frequency 1 over 10. The frequency 1 over 10, our progression concentrates in this congruence class, this point, whereas the interval spreads around all the possible congruence classes mod 10. And the middle interval, again, which didn't satisfy the naive heuristic, well, its Fourier transform is very large at 1 over 200. At that frequency, you get all the points pointing in the same direction, whereas for the full interval, it all spreads nicely around the unit circle. Okay, so we can account for the Bohr structure in our previous examples using this Fourier uniformity test. If you're not Fourier uniform, then you do concentrate in a Bohr translate. So we show in the notes, if you've got a set which is not epsilon Fourier uniform, then you can find a Bohr translate in your interval such that the intersection of your set with this Bohr translate is substantially bigger than what you'd expect from a random model. So if this set was equidistributed in Bohr translates, you'd expect this intersection to always be around this number. But because you're not epsilon Fourier uniform, there is some translate where you get this extra proportion of points, a positive proportion of your points in this set lie in this Bohr translate above and beyond the naive expectation. So Fourier non-uniformity definitely exhibits Bohr structure. And you can show the converse that if you're sort of equidistributing Bohr sets, if you're not equidistributed in Bohr sets, then you don't pass the Fourier uniformity test. But we don't do that. We don't pursue that in this course. But the most important facet of Fourier uniformity for us is that if you're Fourier uniform, you do satisfy the naive heuristic. So here's a proposition. We've got a set of density delta. Let's assume it's epsilon Fourier uniform. Then the number of solutions to our equation in this dense set is equal to the number of solutions in the interval weighted by the density cubed plus an error, which is epsilon, the level of Fourier uniformity, times n squared, and n squared is the order of magnitude of this. So the number of solutions in the interval is half n squared, 1 plus little over 1, as n tends to infinity. So what that means is, for epsilon sort of polynomially small in terms of delta, you've got the naive heuristic. This is genuinely an error term. You can forget about it, and you've got this asymptotic formula. So Fourier uniform sets satisfy the naive heuristic. So let's prove that. So we want to compare these two sums, and using a telescoping identity, or not this exact telescoping identity, but one of this flavor, you can compare a product, a difference of products to products containing differences of individual factors. And why is that a good thing to do? Well, we know our set A is Fourier uniform, so we know the Fourier transform of this is comparable to delta times the Fourier transform of this. So we want to get that difference in somewhere. So let's do that. So we just use standard telescoping trick to rewrite our difference of sums, or our difference of products, in this way. So we call each of these, this function here, the balanced function of our set A. It's the indicator function of the set minus the normalized indicator function of the interval. This has got mean 0, so we call it balanced. And this difference here can be expressed as 3 sums. And in each sum, we're counting solutions to an equation where one of the functions is weighted by a balanced function. One of the variables is weighted by a balanced function. Okay. Now, I want to show that this is equal to this up to some error term. So all of these individual summands have to go into my error term. So I want to show each of these individual summands is small. Each of these individual sums. How do I do that? So we'll do it via a Fourier control lemma. We'll show that the Fourier transform of our functions controls a weighted count of the number of solutions to our equation. So if you've got some one-bounded functions bounded in magnitude by 1, and you're counting solutions to your equation where the variables are weighted by these functions, then that count is controlled by the L infinity norm of the Fourier transform of any of the functions times a factor of n. So why is this useful? Well, we've got this kind of situation. We want to control a sum like this where one of the variables is weighted by the balanced function. And we know how the L infinity norm of the balanced function, or the Fourier transform of the balanced function, behaves. So we apply this lemma and we can control this sum using the L infinity norm of the Fourier transform of the balanced function times this factor of n, and our set is Fourier uniform. So this L infinity norm is at most epsilon times n by the definition of Fourier uniformity. So do go and revise that if it hasn't stuck in your head since the slide where we introduced it. Okay, so that's why this Fourier control lemma is useful. How are we going to prove it? Well, we'll first observe that if we take these homomorphisms evaluated at some fixed integer n, and we integrate them over all possible frequencies, we obtain a delta function. And that delta function detects whether our integer is 0 or non-zero. So we're trying to count solutions to our equation weighted by these arbitrary functions. Let's remove this constraint here by introducing the delta function. So we detect when this equation is satisfied by applying our delta function to the linear form x plus y minus z. Now integration is linear, so we can take it to the outside of this sum, and you obtain an integral over the Fourier transforms of each of our individual functions. Now one of them has a twisted coefficient, a coefficient of -1 of the frequency, and that comes about from the fact that the z variable here appears on the other side. So we're analysing the equation x plus y minus z is equal to 0. Okay, so we hit this summation with the orthogonality relations. And now we just apply Holder's inequality to the integral. So we extract the L infinity norm of the Fourier transform of the first function and the L2 norm of the Fourier transforms of the second two functions, second and third functions. How do you bound the L2 norm of a Fourier transform? Use Parsifal's identity, which is really just another instance of the orthogonality relations. And it's a nice exercise. I encourage you to go and do it to show that these L2 norms are at most n to the half each. So that's where our factor of n comes from. And there's nothing special about the function f1 here. This could have worked for the function f2 or f3, so we can have any index we want here. So that implies this proposition that we stated, that the Fourier uniformity implies the naive heuristic. And you can state it more generally. For a general linear equation, we've got a set of density delta, it's epsilon Fourier uniform, and we should assume that there's at least 3 variables and all of these coefficients are non-zero integers. Then you essentially get the naive heuristic. The density to the power of the number of variables times the number of solutions to the equation in the interval plus some error depending on the level of Fourier uniformity, where n to the s minus 1 is sort of a good guess for the order of magnitude of this sum. Now, there's a number theoretic problem here to show that this thing does have that order of magnitude, and you know, normally you can show that this thing here is either going to be like 0 if there are no solutions, or if there's no obstructions to having solutions, it should be sort of order of magnitude n to the s minus 1, up to some implicit constants depending on the choice of coefficients and constant b. So in this latter case, we do have the naive heuristic if you take epsilon small enough in terms of delta. Okay. So that's great. We can always count solutions to equations in Fourier uniform sets. In fact, we can obtain an asymptotic formula. And most sets, a random set is Fourier uniform, you can show that. So most sets are Fourier uniform. So almost all of number theory is solved. Brilliant. Unfortunately, most interesting sets, most interesting dense sets, are not Fourier uniform. And maybe that's not surprising, because if a set is interesting, we've probably constructed it in some algebraic way or some deterministic way with a little bit of algebra. And so it's likely to have some algebraic structure. So what do you do? So here's a possibility, and this is something we'll prove next time, that if you're given a dense set A, you can run something called a density increment argument to find a long progression where your set hasn't lost any density. And hi Peg, I'll be down in a second. I'm just finishing a recording, okay? Where was I? So your set is dense on the progression, and it's Fourier uniform on the progression, which is brilliant. So using this procedure, you can say, well, okay, I'm not going to count solutions to my equation in my original dense set, but I'm going to count solutions to my equation where the variables are constrained to the intersection of my dense set with this subprogression. And there I've got Fourier uniformity, so everything behaves nice and randomly. I should get the naive heuristic. That's great if you haven't destroyed your solutions, the solutions to your equation, by passing to this subprogression. So imagine if your set behaved randomly, it was Fourier uniform on the odd numbers. So you pass to the odd numbers, but you can no longer exhibit any solutions to your equation, because by passing to the odd numbers, you've destroyed all possible solutions to your equation. So that's kind of coming down to this fact that we saw earlier, that the number of solutions in the interval could be 0. And the same is true for a subprogression. Okay. But for that equation, for x plus y equals z, that's bad news. But there are equations where you don't destroy solutions by passing to a subprogression, e.g. the equation of 3-term arithmetic progressions. And indeed, for any equation which is called translation invariant, i.e. all the coefficients sum to 0, what you can do is you can always pass to a subprogression and solve your equation there. So for these translation invariant equations, you can always obtain the naive heuristic on some subprogression. Great. So that's what we'll do next time.